Hi, welcome to the Arcade School. This week the Arcade School's in Yuma, Arizona, and I'm here at Lutz Casino to see if I can borrow some XY games from my friend Bill Lutz. As you know, when the Arcade School travels to the various cities across the country, we always try to borrow the latest games so that students can gain valuable hands-on experience working on the very latest equipment. Well, Lutz Casino isn't really a casino at all. In fact, it happens to be the oldest continually operating pool hall in Arizona. So let's go inside and see if we can contact my friend Bill Lutz. Hi, Bill.
Randy Fromm, what a surprise. What brings you to Yuma?
The Arcade School.
Sit down and tell me about it.
Yeah, Bill, the Arcade School's in Yuma this week. I really thought you'd have heard about it because I sent a flyer to just about everybody. In fact, to be honest with you, that's really why I'm here. I was hoping you might be able to loan me an XY game for the school this week.
You bet.
Good.
I'll tell you what, I'm not that familiar with the XY system, and I'm not really sure which games are XY.
No kidding. You have a Tempest and an Asteroid, don't you?
Yes?
Well, Tempest and Asteroid are both XY games. Do you think there's any chance I might be able to use one or both of those?
Oh, for sure. Hey, in fact, my other game room is closed for remodeling,
Yeah?
and you can have your choice of any of the games.
Gee, I didn't even know you had another game room.
Yeah, and if you have the time, we can go there now, and you can pick out the games you want.
Huh, no kidding. Yeah, I have some time.
Hey, well, let's go.
All right.
Hey, I got something for you.
Oh, yeah, what? Oh, hey, it's one of your Lutz Casino hats. Great. Thanks a lot. I'll tell you what, when we're over there at the arcade, I'll show you how you can determine if your game's an XY game. Well, Bill, you can easily tell the difference between an XY and a raster scan system just by looking at the screen. I think you're pretty familiar with the raster scan system, aren't you?
Pretty much.
Well, you know how, for instance, in Pac-Man, which of course is a raster scan game, when you see the Pac-Man, you not only see the image of the Pac-Man, but you see that he's filled in solid yellow, right? Well, if you look at the screen in an XY game, like this asteroid here, you see the objects on the screen like these asteroids, but all you see is an outline of the object. You see it's not filled in solid at all. It just looks like the beam is drawing the object directly, but doesn't fill it in. And in fact, that's really how it works. So it's really easy to tell the difference between a raster scan and an XY just by looking at the object on the screen. If it looks like the objects are filled in solid with color, it's definitely a raster scan monitor. And if, on the other hand, the objects are simply made of lines but they're not filled in at all, then it has to be an XY. I'll tell you what, I don't have any service calls this afternoon. Why don't I just take a little time and I'll run through the whole XY system for you, just like I do at the Arcade School. It's really pretty simple, and I think you'll probably get a lot out of it.
Great, Randy. I'll take some notes, too.
Okay, why don't you just sit down and get some paper and a pen, and we'll go through this thing one step at a time, and you'll see it's really an easy system to work on. In fact, the XY system's even easier to fix than the raster scan. In the XY system, instead of having a beam that constantly scans back and forth, the computer actually tells the beam directly where to go. The beam really starts out right in the center of the screen, and the computer tells the monitor to move the beam left or right or up or down and draw the picture that you see here. Depending on what's being drawn on the screen at the time, the computer will send out different signals to the monitor. In asteroids, for instance, the rocket ship starts out in the center of the screen. The beam that draws the rocket ship actually moves from point to point and draws just the rocket ship. And then the beam is turned off, and it's moved to the next nearest object, say an asteroid. And it goes to the middle of the next nearest object and then moves out to the edge and draws that object. And then again, the beam is turned off and quickly moved to the next nearest object, and it draws that object. Then maybe moves up and draws the score, and so on. The computer actually tells the beam directly where to go on the face of the picture tube. And if I turn up the brightness, you can actually see how the monitor paints the picture. Watch this. Do you see the connect the dots pattern here? Do you see how the lines travel in between each individual asteroid on the screen? You can see how the beam moves from point to point to point, drawing the line as it goes. Well, naturally, we don't normally see that connecting line. because we've turned the brightness up here, and naturally we see it because the brightness is up so high that, in fact, it's not turned off the way it should be. I'm not going to leave this on here too long because there is a possibility that we can burn the phosphor right here in the center where you see that very bright dot. So I'm going to turn down the brightness here and turn it down a little bit more, a little more, and of course that's the normal picture there. So the XY system works in a completely different way than the raster scan system. In the raster scan system, the beam is constantly scanning back and forth. But in the XY system, the computer actually tells the beam directly where to go on the face of the screen. The picture tube in an XY monitor is the same as the picture tube in a raster scan monitor. There's an electron gun back there that shoots out electrons that strike the front of the screen, making the phosphors glow. Also on the neck of the picture tube, there's a yoke coil. Remember, the yoke is actually made of two different coils, one that makes the beam move left and right, and one that makes the beam move up and down. And it's the same on the XY as it is in the raster scan. But we don't call the coil that makes the beam move left and right the horizontal deflection coil the way we did in the raster scan system. In the XY system, we give that coil its algebraic name. We call that horizontal direction X in the XY monitor. So that coil that makes the beam move left and right is known as the X deflection coil or the X yoke coil. Also, the coil that makes the beam move up and down is not called the vertical deflection coil as it was, again, in the raster scan. In the case of the XY monitor, the coil that makes the beam move up and down is called the Y or the Y deflection coil. And that's why we call it the XY system, because there are actually signals that come from the computer that tell the monitor where to move the beam left and right and up and down. Now naturally, since we don't see the connect the dots type of pattern all the time as the beam moves from object to object, somehow we have to turn the beam off in between the different objects. Well, in the raster scan, we had a signal that came from the computer that turned the electron gun on and off. Remember, it was called video, and the video signal made the gun turn on and off and made certain areas of the screen lighter or darker. Well, we have a similar signal that comes from the computer in the XY system, but we don't call it video. In this case, we call the signal that turns the electron gun on and off, a signal that comes from the computer, the Z signal. And in the monitor itself, instead of having a video amplifier, we have the Z amplifier. So in the XY system, we have X making the beam move left and right, and Y making the beam move up and down, and Z that turns the electron gun on and off. Of course, in the color XY system, there are actually 3 Z signals, one for each color, because like in the raster scan color monitor, there are 3 electron guns, one for red, one for green, and one for blue. So the 3 Z signals come from the computer and tell the monitor what colors to turn on. Red, green, and blue, remember, are the 3 primary colors of light, and it's the same in a color XY system as it is in a color raster scan. The X, Y, and Z signals for the monitor come from the computer and are simply carried by 3 individual wires that connect the computer to the monitor. The X and Y signals coming from the computer may be either positive or negative depending on what the computer wants the monitor to display. And in the monitor itself, 2 identical deflection amplifiers, one for X, one for Y. So in the XY system, we have 2 virtually identical amplifiers, one for the X deflection, making the beam move left and right, and one for the Y deflection, making the beam move up and down. Well, remember in the raster scan system how the horizontal deflection section was working much, much faster than the vertical deflection section. Well, in the XY system, they're both about the same, and they both work at quite a bit slower speed than in the raster scan monitor. Depending on what the computer's doing at the time, the approximate speed of the X and Y deflection circuits are about 40 cycles per second. To drive the deflection circuits, the XY monitor uses a split power supply. The positive and negative outputs of the power supply are used to power the deflection amplifier, and this is the schematic circuit for the X deflection amplifier. Remember, X and Y are both identical, so we'll take a look at this amplifier. The positive power supply, shown here in the upper left-hand corner as B+, is connected to the collector of one of the output transistors. There are actually two output transistors in each of the X and Y amplifiers. The emitter of this transistor is then connected through a fuse to the X yoke. Also, in the bottom left-hand corner, the B- or negative supply is connected to the collector of the second output transistor. This one happens to be a PNP transistor, where the first one was NPN. The emitter of the PNP transistor is also connected through the same fuse to the X yoke. So, in the XY system, the monitor uses that split supply to make the beam move left and right. If the monitor wants to make the beam move to the left, it uses negative current and runs negative current through the X yoke, and that makes the beam move to the left. If the monitor wants the beam to move to the right, it uses positive current, and the positive current goes through the same X yoke, but because the current direction's reversed, the polarity of the magnetic field has been flipped. It's the same for X and Y, and it's the same for black and white as it is in a color monitor like this one here in Atari's Tempest game. This is a color XY monitor, but as far as the deflection circuits are concerned, X and Y are virtually identical. It's the same situation where negative current will make the beam move to the left and positive current will make the beam move to the right in the X section. But remember, in Tempest, the monitors turn sideways, so that in fact this direction is actually the X direction. Remember, we saw this in the raster scan monitors. As far as the monitor itself is concerned, X is X and Y is Y. The monitor doesn't care if it's installed sideways. And remember, the way you can tell if the monitor's turned sideways in the game or not is that normally a picture tube is wider than it is tall. The output transistors that drive the X and Y deflection coils are located on the chassis of the monitor. To make the beam move to the right, the NPN transistor in the X section is turned on. This allows positive current to flow through the yoke. In the Y section, the NPN transistor makes the beam move up. If the PNP transistor in the X section is turned on, negative current flows through the yoke and the beam moves to the left. And in the Y section, the PNP transistor makes the beam move down. Suppose you're working on an asteroid and this is your symptom. Well, just by looking at the screen, we know right away this is definitely an X deflection problem. We're missing the entire left half of the screen. What we see here is it's completely filled out in the vertical direction, which of course is Y, remember, and it's missing the entire left half of the X section. So right away we know that it's an X problem, and because we know what the output circuitry looks like, we know that it's the PNP transistor in the X deflection circuit that controls the left half of the screen. What if your problem was this? Well, here again we have an X problem, don't we? We're missing half the screen, and in this case we're missing the right half of the screen. So we definitely know it's still an X problem. In this case, it would be the NPN transistor in the X deflection circuit. If we had a problem in the Y deflection section, you might see something like this. Again, we're missing half the screen. In this case, we're missing the bottom half, aren't we? And remember, the PNP transistor controls the bottom half as well as the left half of the screen. So in this case, it has to be the PNP transistor in the Y deflection section. And of course, a problem like this is also a Y problem. In this case, it's the positive half, or the top half of the picture, which is controlled by the NPN transistor in the Y deflection section. In this case, we have just the upper right-hand corner of the screen visible. This particular symptom is caused by failure of both PNP transistors, the one in the X and the one in the Y deflection section. In the X section, the PNP transistor controls the left half, and the left half of the screen is missing. In the Y section, the PNP transistor controls the bottom half, and the bottom half is missing as well. So in this case, because the left half and the bottom half is missing, we know that both of the PNP transistors are at fault. It's a problem in the X section and the Y section. So you see, it's easy to diagnose deflection problems in the XY system. And it doesn't matter whether it's battle zone or asteroid or even the color monitor in this Tempest game. The deflection circuits are always the same. And if you're missing half the picture, well, go to the output transistors in the deflection section and test the output transistors. Whether it's the PNP or the NPN doesn't make any difference. You still test the transistor the same way. And if you find that you have a bad output transistor, and say you replace it and you still end up with the same symptom, well, just check the rest of the parts in that particular amplifier. If you're missing the right half of the screen, you know it's an X problem. If you've replaced one of the output transistors in the X deflection section, and you fire the game back up and you have the same problem, simply check all of the other transistors and resistors and other components in the X amplifier. It certainly doesn't make any difference at all if we know how the amplifier works. Once we've isolated the problem down to the X amplifier, all we have to do is use our meter to test all of the parts in that particular section. The X and Y output transistors are mounted on the side of the chassis, but the rest of the X and Y amplifier circuitry is mounted here on the deflection printed circuit board. In the color XY monitor, the deflection amplifier circuitry is located here on the bottom of the chassis. But what would happen if you were missing, say, the entire X deflection amplifier? Say both the NPN and the PNP transistor in the X deflection amplifier failed. What do you suppose the symptom would be? Well, most people would think that if both halves of the X deflection circuit went bad, you would simply see a vertical line because there would be no horizontal or X deflection. But in fact, you won't see anything at all. The reason you won't see anything at all if you lose both the NPN and the PNP transistor in one deflection amplifier is that if that were allowed to happen, you'd see something like this. Or if the computer itself failed, or the 5-volt power supply that powers the computer, you would see a spot like this, right in the center of the screen. Well, in either of these cases, the phosphor coating on the inside of the picture tube would be severely burned because the beam is in one spot, and this extraordinary brightness that you see will actually cause the phosphor coating to be destroyed over a very short period of time. Well, to prevent that from happening, the engineers that designed the monitor included a circuit called a spot killer circuit. Well, the spot killer circuit is there so that if we lose both halves of the deflection in either the X or the Y amplifier, or if the computer goes down and we have no X or Y deflection signals at all going to the monitor, the Z amplifier is turned off by the spot killer circuitry. By turning off the Z amplifier, which remember controls the electron gun, we essentially cut off the electron beam. And by cutting off the electron beam, there's no way the phosphor will be damaged, because with the beam cut off, there's no brightness at all. The spot killer circuitry is extremely important to the monitor, and it's very important to understand how the spot killer works and how we can know that it's been activated. In this case, the spot killer LED right here on the side of the monitor on the deflection printed circuit board indicates that we have a loss of deflection. If this light emitting diode is illuminated, we know that we have a loss of deflection somewhere. We don't necessarily know if it's in the monitor itself, meaning one or both of the deflection amplifiers have failed, or perhaps the signal's not coming from the computer. We'll see how to determine that in just a second. But for the moment, by looking at that spot killer LED and seeing that it is on, we know we have a problem with loss of deflection. And by having the spot killer circuitry there, it can shut off the Z amplifier and prevent any damage from occurring to the phosphors that coat the front of the screen. When a loss of deflection has activated the spot killer circuitry, the spot killer LED on the deflection printed circuit board will be illuminated. When the LED is on, the spot killer circuit is on too. So when the spot killer circuit is activated, it turns off the Z amplifier, which of course in turn turns off the electron gun and prevents any electrons from reaching the front of the screen and burning the phosphor. And that's real neat, but now we have to determine where our loss of deflection has occurred. In other words, perhaps both the NPN and the PNP transistor in the X or the Y channel have failed in the monitor, or maybe the computer has failed and it's not sending out the X and Y signals. So it's really important before we start ripping the monitor apart, testing all the transistors and the deflection circuits, to find out if the problem really is in the monitor or not. And there's an easy way to do that. Right here in the monitor is the connector that carries the X and Y deflection signals from the computer up to the monitor. And remember, these signals are just positive and negative voltages depending on where the computer wants the monitor to show the particular dot on the screen. Well, since the voltage coming from the computer is both positive and negative, that's AC, isn't it? And we can check to see if we have the proper inputs to the monitor by measuring the AC voltage at the input connector on the monitor itself. All we have to do is connect our meter to the input connector. And of course, we'll ground the black lead and set our meter to the 20-volt AC range. We'll insert the red meter lead into the X or the Y inputs on the connector and simply measure the voltage. If we have this changing AC voltage that you see here, we know that we definitely have a good input to the monitor. And what you're seeing here is the voltage change depending on what's on the screen. Right now you see that the voltage is jumping around as the different asteroids come and go across the face of the screen. And when you see this particular reading, you know that you definitely have a good AC input coming from the computer. And if the spot killer is on, you know that the problem definitely lies in the monitor. If, on the other hand, we tested the input voltage to the monitor at the X and Y inputs, and we saw no voltage at all, or we saw a DC voltage instead of an AC voltage, well, we know that the problem was not in the monitor. You can't expect the monitor to work properly if the computer's not putting out the right signal. Here's a little trick that you can use to help localize a monitor problem when the spot killer is on, but the X and Y inputs from the computer are good. Turn up the brightness on the monitor and look at the front of the screen. If you turn up the brightness and see a vertical line, then your problem's in the X deflection section. If you see a horizontal line, obviously your problem is in the Y deflection section. Most operators know that their most popular games don't stay looking new very long. Wear and tear on the control panel caused by hours of use by players can cause the control panel to look something like this in a very short time. But you don't have to suffer with games that look like this, because now there are special replacement overlays that are available from Wico. The overlay is installed by removing the control buttons and putting the self-adhesive overlay right over the worn control panel. After the buttons are replaced and the game is secured, the game looks as good as new. Replacement overlays are available for most of the popular games today, as well as replacement side graphics. These fine, high-quality overlays are manufactured by Willis Graphics expressly for Wico. So contact your local Wico representative or call Wico on their toll-free order line for details. Since the picture tube in an XY game is the same as the picture tube in a raster scan system, we need the same kinds of high voltage to operate these picture tubes. The black and white XY system needs about 12,000 volts, and the color XY system about 20,000 volts to operate properly. Well, remember in the raster scan system how the horizontal deflection circuit was used to drive the high voltage unit. And that high-pitched squeal that we heard told us that not only was the horizontal deflection circuit working properly, but that the high voltage was there as well. Well, in the XY system, the high voltage is completely separate from the deflection circuits. There's a separate high voltage unit in the XY monitor that has absolutely nothing to do with the X or the Y deflection circuits. So let's take a close look at the high voltage unit in the XY monitor. This is the high voltage unit in the black and white monitor. And in the color XY monitor, the high voltage is here in this unit. And this wire carries the high voltage up to the second anode. Remember, the picture tube will store a charge. If you remove this connector, don't forget to discharge the picture tube first. This is the high voltage transformer, and this is the high voltage rectifier in the black and white high voltage unit. This is also known as the EHT unit, meaning extremely high tension. If we look at the schematic of the high voltage unit, you see that it creates not only a 12 kilovolt supply that powers the second anode, but also a 400 volt and a 90 volt power supply. Well, these power supplies are used to power other circuits in the monitor. The high voltage unit is powered by the same 40 volt power supply that powers the deflection amplifiers, and uses that 40 volts to create our plus 12,000 volt, our plus 400 volt, and our plus 90 volt outputs. This connector carries the 40 volt input to the high voltage and also the 400 volt and the 90 volt outputs. The high voltage circuitry itself is really pretty simple. The entire circuit consists of just 4 transistors, 2 Zener diodes, and a small handful of other components. Do you recognize this standard series pass regulator circuit? Look, this is the series pass regulator transistor. Here's the transistor that drives it, and this transistor and this Zener diode, which are used to keep the voltage constant. In the raster scan system, there were a couple of easy ways we could tell if we had high voltage or not. One way was to simply listen for the high voltage. If we heard that high voltage squeal, that high-pitched, high-frequency squeal, we knew that our high voltage was there. Also, the other surefire method with the raster scan system was to simply look at the neck of the picture tube, and if the heater, the filament that heats up the electron gun in the picture tube, was lit, and you could see the orange glow, well, you knew that you had high voltage because that heater was driven off of a winding on the flyback transformer. But in the XY system, we're not so lucky. Number one, the filament or heater in the neck of the picture tube is not driven off of the high voltage. Instead, the heater is driven off of a separate winding on the power transformer in the bottom of the game. So looking at the filament will only tell you if you have the 6 or so volts AC that it takes to operate the filament. Also, we cannot listen for that high-pitched squeal. In the raster scan system, the frequency of the horizontal section was around 15,000 cycles per second, and we could hear that all right. But in the XY system, the high voltage unit operates at a much higher frequency, somewhere around 30,000 or 30 kilohertz. That's 30,000 cycles per second. And that's way beyond the range of our hearing. So you cannot hear the high voltage work in an XY system. So to test the high voltage in an XY system, you're really quite limited in terms of the number of different methods you can use. One method you can use is to use something like this. This is called a high voltage probe. And what this really is a precision 1000-to-1 voltage divider. The probe plugs right into your meter, right here into the volts and ohms and common jack. And one side of the high voltage probe is grounded, and the probe tip is inserted underneath the cap of the second anode connector. When the monitor is turned on, you can read the voltage right on your meter. For every 1,000 volts that appears here on the tip, we get a 1 volt reading on the meter. And in this case, you see we have 12 volts listed here on the meter, so naturally the high voltage is really 12,000 volts. Using the high voltage probe to check the second anode voltage is certainly a very accurate way to check that EHT output. But here we're measuring a very high voltage with the power on, 12 or 20,000 volts. And if there's another way to check the EHT output without measuring such a high voltage, it would certainly be better to do it that way than to go ahead and use the high voltage probe to check the second anode. And there is, naturally, a better way to check the EHT output. Because remember that the EHT unit creates not only that 12,000 volts, but also a 400 volt and a 90 volt power supply. Remember that 90 volt power supply is used to power the Z amplifier. Well, certainly 90 volts is a hell of a lot lower than 12,000 volts. And if we can measure that 90 volts and see that it's present, we can determine that the second anode voltage is there. So that's what we'll do. Instead of checking that very high voltage at the second anode, we'll simply check the 90 volt output from the EHT unit itself. Checking the schematic, we see that the 90 volt output comes from pin 5. And we can check that 90 volt output from the EHT unit by setting our meter to the 200 volt range and inserting the meter lead into pin 5 of the connector. Here you see the correct reading, so chances are really pretty good that we have high voltage. The EHT unit in the XY system is really pretty easy to understand. And remember, to test the EHT output, we're going to check the voltage at the 90 volt output. And if that 90 volts is there, we know we have high voltage, and if it's missing, we know that we don't have high voltage. Well, if you do test the 90 volt output and find that the 90 volts is missing, before you rip the EHT unit apart to find out what's wrong with it, check the 40 volt input. Well, naturally, the EHT unit won't work if the 40 volts, that is the input that powers the unit, is missing. Remember, garbage in, garbage out. And we won't get the EHT output if we don't have any 40 volt input. But if you check the 90 volt output and it is missing, and you check the 40 volt input and it's there, you definitely know that the problem is in the EHT unit. Once you've found that the problem is in that unit, repairing the EHT unit is a simple matter of turning off the monitor, removing the unit, and using your meter to check all the parts in the high voltage section. Generally speaking, most of the parts are fairly reliable, and there's only a few transistors that might possibly fail. Well, quite frankly, I find very few component failures in the black and white EHT section. Most of the time, when I have a high voltage failure in a black and white monitor, the high voltage failure can be traced to the connections between these two transistors here on each side of the EHT unit and this small socket here mounted on the printed circuit board. The transistor is mounted on the side of the unit and its leads are inserted into the connector. Sometimes the connection between the transistor leads and the connector go bad. When that happens, you might have a low high voltage condition, or you might be missing your high voltage completely. Well, we know that if we're missing high voltage, we don't see anything at all on the screen because we need the high voltage to remove those spent electrons. But what do you suppose the symptom would be of low high voltage? Well, believe it or not, the symptom of low high voltage, or low EHT, is a picture that's very large, much larger than normal. Now, that may surprise you. This symptom, which is called blooming, seems unusual for a low high voltage condition, but in fact, this is what you'll see. Now, most people think that you would see a shrunken or dim picture, but remember, the EHT is there to remove those spent electrons. And if the high voltage is just not quite high enough, it leaves some of the electrons in the picture tube. And those electrons will cause the electron beam to be deflected out to all of the sides of the monitor. So if you see a symptom like this, suspect loose transistors on the EHT unit. I repair the loose connections by using my small screwdriver to gently push the leads of the transistor further into the socket. This improves the connection between the leads and the socket itself. The high voltage unit in the color XY monitor can be tested for proper operation with the high voltage probe as before, or by measuring 181 volts on pin 5. If you've determined that you're missing the high voltage by checking the 90 volt output of the monitor, but when you check the 40 volt input you find that it's missing as well, you certainly don't want to tear the EHT unit apart. The problem's not there. So let's take a look and see where the EHT unit gets its 40 volt input power. The power supply for the high voltage unit is labeled EHTB+ and comes from pin 6 on the deflection board. If we follow this line back, we can see that the EHTB+ has first passed through diode D100 and fuse F102. The actual B+ itself comes from the bridge rectifier, the same bridge rectifier that powers the deflection amplifiers. Here's diode D100. It's located right above the bridge rectifier on the deflection printed circuit board. And here's F102. By the way, here's an easy way that you can check the output of the bridge rectifier. The positive and negative outputs of the bridge are connected to the collectors of the deflection output transistors. We can measure the positive output at the case of one transistor and the negative output of the power supply at the case of the other transistor. As long as you see the voltage, everything's fine. The XY monitors that we use in video games are made by two different manufacturers, Electro-Home and Wells Gardner. If you have a high voltage problem with your XY game and you've determined that you're not only missing the 90 volts out, but you're missing the 40 volt input as well, check to see if you're working on a Wells Gardner monitor with two large power resistors on top of the deflection printed circuit board. These resistors are connected in series between the output of the bridge and the rest of the monitor circuit, and they're notorious for open circuiting. When the resistor opens, it cuts off the current flow to the rest of the monitor. Resistor number 101, the resistor that's in series with the B+ line, is more often the one that you'll find open. And the reason for that is that the positive power supply powers not only the deflection circuit, but also the EHT unit. And since R101, which is in series with the B+ line, has more current being drawn across it, it's usually the one that fails. Well, there's a real easy clue that you can get that will help you zero right in on this particular failure. In a normally working XY monitor, as the current passes back and forth through the yoke, you can actually hear the yoke making a kind of a clattering sound or a buzzing sound. And in fact, this sound which comes from the yoke is called yoke clatter. If you can hear the yoke clatter, you know that the deflection circuits in the monitor are working properly. If, on the other hand, you don't hear the yoke clatter, you know the deflection circuits are not working properly. Well, if you get to a monitor and you see there's no picture at all, and you look at the spot killer and it's off, listen to the yoke and listen for that yoke clatter. If you do hear the yoke clatter, it means the deflection circuit's working all right and the B+ and B- supplies are okay as well. In that case, you would suspect a high voltage failure. But if the spot killer LED is off and you do not hear the yoke clatter, and if you're working on a Wells Gardner monitor with those two large power resistors, immediately suspect that those resistors are open. Just one more point of interest as we conclude our look at the XY monitor system, and that is this. If you do find that one or both of those power resistors on the deflection board have open circuited, instead of replacing the resistor, the monitor manufacturer recommends that you simply short the open resistor with a piece of heavy wire. But that's really it as far as our look at XY monitors is concerned, Bill. I hope I've answered some questions for you.
Sure have, Randy. Thank you. You make it very simple.
Well, it really is simple, and thanks again for the hat. And thank you for watching.